I will talk about so-called the non-homogeneous Poisson process. So non-homogeneous Poisson process, as I said that for the Poisson process, whatever we discuss, there that lambda intensity, it is independent of time. So question is, what happen if lambda depending on time? In particular, for simple example, suppose you look at some coffee shop, okay, in the cafeteria. So you see that in the morning time, more people are coming, okay, and then in the evening time also more people are coming, but in the lunch time there are less people. That means depending on the time. So this lambda is basically the intensity. So the people are coming with rate, that is the intensity. So there it is depending on the time. So which time actually we are considering, whether it is morning time, it is lunch time, or it is evening time, and so on. So in real life situations, non-homogeneous Poisson process comes into picture. For this example, as I said that in the cafeteria, people are coming, suppose in a Poisson process with intensity say lambda t, that depending on t. Okay, so let us give a formal definitions of a non-homogeneous Poisson process. So it is exactly similar to that NT, but here lambda should depend on T. So it's a Markov process. Okay, it's a Markov process. I say that NT such that T is positive, okay, is called non-homogeneous Poisson process. So with intensity function now. So because what we have seen that lambda is positive. So in this, that is why I want to find this lambda t. This should be a function, or lambda is a function from 0 infinity to 0 infinity. Okay, so this is a positive functions, okay, or non-negative functions, such that it satisfies this property. N of 0 is equal to 0, and second is that NT, this has independent increment, okay, it has independent increments. And what is the third thing, that if you consider for s less than equal to t, look at the random variable nt minus ns, it has a Poisson distribution, with parameter, this is s to t lambda u of du. Okay, so that is what I can write down, that probability of nt minus ns is equal to say k. This should be, since it follows a Poisson distribution with parameters, these things, what I can write down, this is my s to t, okay, lambda u du all to the power k by k factorial into the power minus this quantity, integral over s to t lambda u of du. Okay, now you see that if my lambda is independent of time, then it gives you the Poisson process, or sometimes we call the homogeneous Poisson process, or simply the Poisson process, is it not? So here only thing is that the intensity depending on time. So intensity now a function, okay, it's a non-negative function. Okay, so for example, as I where one can use this non-homogeneous Poisson process, I already told you that here actually people try to use the non-homogeneous Poisson process. I can consider one more example, but spirit in a same way. Okay, so a store opens at 8 a.m. Okay, from 8 to 10 a.m. that customers they arrives at a Poisson rate of 4 an hour. Okay, means from 8 to 10 customer arriving at a Poisson rate of lambda is equal to 4 per hour or at hour. Okay, then from 10 to 12, from 10 to 12 their lambda is equal to 8. Okay, now from 12 to 2, now it is steadily increasing from 12 to 2 means 14 I can say, because if I think of whole day as a 24 hours, so from 12 to 14, that's means from 12 to 2 it's steadily increasing, it's steadily increasing from 8 power 8 per hour at 12 to 12 per hour at 14. Means from 12 to 2 it increases from 8 to 12, steadily increases. Okay, that means at 2 if you see that there are 12 per hour. Okay, and at 12 it was 8 per hour and steadily increases. And again from 2 to 5 means 70s, it steadily decreases from 12 per hour to 6 per hour. So this is 6 per hour at 5. Okay, that means from 2 o'clock, so it was 12 per hour, then it steadily decreases to 6 per hour at 5. Okay, and then now suppose that after that my shops are closed, so then we want to know, determine the probability distribution of the total number of customers that enter the store on a given day. Okay, so this is the question. So we want to know the probability distributions of the number of customers, or the total number of customers that entered to the store or the shop on a given day. That means what I have to know, since it is a Poisson, follows a Poisson process, it is a obviously non-homogeneous Poisson process because the intensity depending on the time. Okay, so in this case what I have to find out, basically I need to find out my lambda t, is it not? So how I can find out my lambda t? So you see that up to 8 a.m. so it the store opens at 8 a.m. that means I can think of lambda t is equal to 0 for 0 less equal to t less equal to 8, because per hour actually I am looking for, and then it is 4 whenever 8 to 10, is it not? So this is t less than 8, 8 less than is equal to t less than 10, it is 4, and then a when from 10 to 12, and now what it says that from 12 to 2 it readily increases. So I can think of this is my AT plus B form. Okay, it steadily increases. So from 14, from 12 less than equal to t less than 14 up to 2, and then I can maybe ct plus d, it steadily decreases. I want to find a, b and cd. Okay, so from 12 less than equal to t less than say 17, and then maybe 0 after, so 17 less equal to t less than equal to 24 maybe, is it not? So whole day you have 24 hours, and the lambda t intensity function, it is defined in this thing. Then how to find out my a, b, c and d? Because it is given to you that at 12 it is 8, no, and then at 14 it is basically 12. So that means I have 12a, because if you put t is equal to 12, 12a plus b, so in that time it is 8, and then whenever it is 14 it steadily increases to 12. That means I have 14a plus b, so this should be is equal to 12. Is it not? So now if you solve these two equations from here, what do you have? You see that a is my 2, b is my 16. And similarly, I can have, since from 14 to 17, 2 to 5 o'clock, it steadily decreases from 12 to 6 per hour. So whatever I have, that 14c plus d, it is 12, and then at 17c plus d, it is basically 6. So from there actually if you consider c is equal to minus 2, d is equal to 40. So then how your intensity function lambda t looks like, if you write down again, you can find out, no, because you put c and value the a, b, c and d. Okay, so what I want to show, I want to show that this n24 minus n of 0, no. So the total distributions for these things, what will follow? It will follow a Poisson distribution with parameter gamma, which is equal to my 0 to 24 lambda u du. Is it not? Last, just look at the condition 3 from my definitions. Nt minus ns has a Poisson distribution, that is the total number of things, no? Nt minus ns, the Poisson distributions with parameter s to t lambda u do u. So now for a given day, that means it is 24, 0 to 24 of lambda u do u. Now if you calculate this gamma, you calculate yourself, then I hope it should come some 71. That means that the number of customer enter the store on a given day is a Poisson distributed with parameter. So number of customers entered to the store on a given day follows a Poisson distribution with parameter 71. Is it not? So similar kind of examples you can make yourself, as I told you in a cafeteria things and so. So where this intensity depending on the time, no, that is in the real life problem actually we are seeing. That is why this non-homogeneous Poisson process also important to study. Okay. Okay. So then there are many other type of Poisson process. So in particular, if you look at this NT, the Poisson process, okay, we will come back later on. It's not a martingale, not a martingale. I will come back. What do you mean by martingale? In particular, it has three properties. The main property is that if you look at xt given f of t, it should be x of s almost surely whenever my t is greater or equal to s, and ft, this is the filtration. Filtration means basically, so ft, it's a family of sigma algebra. It's a family of sigma algebra or increasing family of sigma algebra, which is subset of A. Okay, this is the filtration. And so expectation of xt given f of t is equal to x of s almost surely. If this happen, we say that process xt is a martingale. So nt we'll check later on whenever I will talk about the theory of martingale, then I will come back. But nt, this is not a Poisson process, this is not a martingale. Okay, and martingale theory has many applications and so on. In particular, one property of a martingale, if you see from here, that expectation of xt given ft is equal to x of s. So if you know a little bit about the conditional expectation, so if you take that again expectation, so what you have here, expectation over xt, and then from the right hand side you have expectation over xs. So that means that expectation is constant, is it not? Expectation is constant. But for Poisson phases, what do we know, that expectation of nt, that is equal to lambda t. It is not constant, depending on the t. If you vary t, then the expectation changed. So it's not a martingale. Okay, because if it is a martingale, then it should satisfy this condition: expectation of xt is equal to expectation of xs for all t s varies in the index set or lies in the index set. So in this case, it's not a martingale. Then question is, can we subtract something so that it will become a martingale? So that is called the centered version of the Poisson process. So maybe definition I can say that n tilde t I denote as, this is nt minus lambda t. I am subtracting this quantity lambda t. This is called the compensator. Okay, so that my n tilde now becomes a martingale. That we will check later on, but this is the main motivation for that. So this lambda t, this is called the compensator of nt, and n tilde, this is called compensated Poisson process. Since you are subtracting the compensator, that is why it is called the compensated Poisson process. Okay, see n tilde, whatever I am defining here, this is called the compensated Poisson process. Okay, and you will see later on this n tilde will be a martingale. Will be a martingale means it's a martingale. Is a martingale. We will check it. Okay, we will check it later. Just looking for these things. Okay, so what is the expectation now? Expectation over n tilde t, since it will be a martingale, so no, you can expect that expectation of n tilde t, it should be constant. And you see, because this is expectation is linear, so you have expectation over nt minus lambda t, hence actually it is 0, because this one we know that it is lambda t, is it not? And what is your variance of n tilde t? This is nothing but variance of nt, is it not? Because this is constant in the sense that it is not random, so variance of non-random things is 0, and hence variance of nt, which is again the lambda t. So expectation of n tilde t, this is 0, so it's constant, no? So you may expect, it does not mean that expectation of some process is equal to 0, it gives you the martingale. There are many examples. Okay, we'll come back later on. In particular, if you look at I'll talk about the Brownian motion. Okay, and then if you look at this b cube t, that expectation of b cube t is equal to 0. In particular, all the odd moment of Brownian motion, okay, that is 0. But b cube t, it's not a martingale. That will come back, okay, later on, because this is, if a process is a martingale, then expectations are constant. But constant expectation does not give you it's a martingale. Okay, in particular, expectation of xt is equal to 0 does not gives you that xt is a martingale. For example, we will see later that the b cube t, where b is a say one-dimensional Brownian motion, it's not a martingale. Okay, this is the compensated Poisson random Poisson process. And then what will be the characteristic function? You check yourself. Phi of n tilde t, okay, at point z, this is given by exponential of lambda t to the power iz minus 1 minus iz. Okay, check yourself, because you know what is the characteristic functions of a process, how to define all these things, and from there actually you calculate. Use these definitions n tilde t, which is equal to nt minus lambda t, and from there you will get it. Okay, so another important thing, that n tilde is not a counting process. Why this is so? Because you see that it may not be integer value, no? Because this is nt, this is integer value minus lambda t. You are subtracting some continuous things or some real number, no? So the difference, it may not be the integer value. Is it not? So it's not a counting process, because if some process be a counting process, then it should be a integer value. Is it not, by definition? So n tilde, or the compensated Poisson process, it's not a counting process. It's not a in general, it's not the integer value. Okay, it's not integer value. It's not a Poisson process, not integer value in general. Okay. Okay. So let us come back another important process, that is called compound Poisson process. So compound Poisson process means basically something like that. Now, suppose the bus running in say Delhi, they follow the Poisson distribution, okay, with some rate. Now that is all buses, okay, follow the Poisson distributions with some rate. Now for each bus, suppose you are coming from say mathematics department to some say Chandni Chowk or somewhere say Rajiv Chowk, okay, by bus. So then actually we are want to know, say at time t, the total number of say customer or the passenger they are shifted. How many customers are shifting from here to there, okay, at time t. That means the occurrence here at any instant of occurrence, it is not a single. Now you have multiple of occurrences, means there are many buses, okay, in a same route, they are going from here to there in some at time instance. So if you look at my bus follows some IID distributed YI, and then what is the total number of passengers? They are basically moving from say department to Rajiv Chowk, that is basically summation over I is equal to 1 to n of t, because that the buses running which follows a Poisson process nt, okay, and this gives you, because in the ith bus if you have y number of say passengers, then this gives you the total number of passengers at time t. Is it not? So that means what I'm saying, that for the Poisson process case, only one event, which occur at instant occurrences. But if there are several events can happen simultaneously, so in that case we call it the compound Poisson process. Okay, so in particular I put as a definition. So is it clear that what is the compound Poisson process? So a stochastic process, say xt such that say t greater or equal to 0 is called a compound Poisson process if xt I can written as summation over I is equal to 1 to nt of yi, where nt is a Poisson process and yi they are iid sequence of random variables and independent of nt. Okay, so why are the IID random variables and independent of nt? As I said that the ith buses actually they are independent, so it follows some distributions and so on. Then if you want to know the total number of passengers carrying for at time t, so then it should be summation over I equal to 1 to nt y of I. Okay, so now if you look at what will be the expectations of xt, because nt and yi's they are independent, so from there what you can say that this should be, because you just consider the conditional on nt and so on, then what you have this should be expectation of nt times expectation of yi and hence y1. Okay, and this is lambda times, because yi is there iid, hence expectation of yi which is same as expectation of y1. Okay, so this is lambda t because expectation of nt is equal to lambda t and expectation of y1. Okay, so if I know the mean of this random variable yi, then I can find the mean of the compound Poisson process xt. And similarly, what will be the variance of xt? Then you will check it should be lambda times expectation over y1 square. Okay, lambda times expectation y1. Just check it. This is nothing but actually just consider xt you write down and then take the conditions on nt is equal to n and with probability nt equal to n and so on, and then you will find out this one. Okay. Okay, so let us consider one example. In my note actually you will see that there are 2-3 examples I have, but I cannot discuss all these 3 examples, so you just look at there. I try to discuss only one example maybe. So now it's a really a good example you can see. First I will write down and then I will discuss. So now customers arrive at ATM. Okay, in accordance to a Poisson process with rate say lambda t. Okay, process with rate say 15 per hour. Okay, so it follows a Poisson process and rate lambda which is 15 per hour. So now suppose that the money withdrawn on each transaction they follow the IID with mean, so the transactions the amount of money withdrawn on each transaction is IID, okay, and it has a mean m say 20 and standard deviation sigma suppose 50, okay. So the amount of money withdrawn on each transactions, it follows IID random variable with mean m which is 20 and standard deviation sigma is equal to 50. So now suppose my ATM is on say 18 hours work, okay. So ATM is on 18 hours work, okay, means if you start from 8 and then it will be go to at night, late night, so the total is 18 hours or 12 hours, whatever you can write down. So for this case I am considering say 18 hours in work, okay. So then question is, what is the total amount calculate the expected amount of total daily withdrawn. Okay, so calculate the expected amount of total daily withdrawn, and then I can also ask the what is the variance, find the variance of the amount total daily withdrawn amount, is it not? So now if you denote yi, which is the amount of money withdrawn on ith transaction, okay, so amount of money on the ith transaction, okay. So assuming that there is no failed transactions and so on, okay, in the ideal case actually we are considering, but real life in a most real life, no, this is not the case, because if there is some problem in your ATM machine, so you may have some failed transaction, but here assume that there is no failed transactions and you denote yi, which is the amount of money in the ith transactions. So then if I denote xt, so this will give you I is equal to 1 to say nt of yi. This is total amount of money withdrawn at up to time t from the ATM, is it not? Because yi, which is the ith transaction amount, the total amount money in the ith transactions, and then that the customers are coming to the ATM in accordance to a Poisson process with parameter lambda is equal to 15 per day, okay, per hour. So nt is a Poisson process and xt, it denotes the total amount of money withdrawn from the ATM at up to at time t. So now what is the question, that daily withdrawn, and my ATM, it is working on 18 hours. So that means I want to find x of 18. This is gives you the total amount of daily withdrawn from the ATM, okay, and this is a random variable. I want to find out what will be the expectation of x18. So then from my I have already seen that expectation of xt, where xt is a compound Poisson process, this is lambda t times expectation of y1. So that means this is lambda is equal to 15, t is my 18, and expectation of y1, which is m, no, that mean that is given to you something is 20, okay. You calculate these things, and then another one, this is my 1, and second, what will be the answering, that I want to know that variance of x18, okay. So this is again by definition, this is 15 to 18, and then expectation of y1 square. So then expectation of y1 square is nothing but sigma square plus m square, is it not? Because m is the mean, sigma is the standard deviations, hence this is 15 square plus 20 square, and then you calculate, something will come, is it not? So this is about the compensated Poisson process, and why this is called compound, sorry, this is about the compound Poisson process. Why this is called compound Poisson process? In particular, if you look at, if you consider yi, which is identically 1, okay, if you look at my yi, which is identically 1, then this xt is nothing but my nt, okay. So that is why this name, that compound Poisson process, okay. In particular, it has a cluster of occurrences at a time, and that is why this is compound Poisson process, okay. So this Poisson process and so on, it is a particular process that is called the Levy process, okay. So I will define so-called the Levy process, but to define that part I need some definitions. Already I have told you. So for that I need the filtrations. Already I have defined, no, ft, in general it is denoted by ft. So that means basically it is a increasing family of sigma algebra subset of f, okay, increasing family of sigma algebra, and we say that is concept called adapted, okay. So xt, it's a stochastic process, okay, and ft is a given filtration. We say that xt is adapted, to the filtration ft if xt is ft measurable, okay. So for stochastic process, what I told you, that for each t, xt, it's a random variable, that means it should be f measurable. But now I am saying that this stochastic process, it is adapted. So see, in general ft is a subset of f, no. So if it is measurability, I am saying there it is measurable here, no, in a bigger space. But now I am saying that xt, for each t, xt should be my ft measurable, okay. Then we say that it is xt is ft adapted. The stochastic process xt is called ft adapted, okay. Okay. So what do you mean by ft measurable? That you already know, no? Because this is all those omega is in my set omega such that x of t omega, this is in my B, this belongs to f of t, where B is the Borel sigma algebra, Borel set. Okay, Borel set from R, because since we are looking for real valued stochastic process, so this B is from, it is a Borel set of R, Borel subset of R, okay. This is the meaning for that. And then can we have, so we can think of this xt as the price of some asset at time t, and this ft you can think of as the information obtained by watching all the prices in the market up to time t. So this is kind of the history of the process, okay. So for example, suppose I have a stochastic process xt, I can define ft such that this is sigma algebra generated by x of s such that 0 less equal to s less equal to t, okay. So this is called the history of the process, and ft is a filtration. So then ft is a filtration. You will see that, and not only that, xt is ft adapted in this case also. It's automatically, by definitions, automatically xt is ft adapted and so on, okay. So this is the sigma algebra, means it is the smallest sigma algebra containing my x or the stochastic process, okay, such that it becomes a sigma algebra. That is a sigma algebra generated by these things. That is the meaning for that. And sometimes this filtration is called the natural filtration. So this filtration is sometimes called the natural filtration. So either filtration is given to you and then we want to show some process is adapted or not. That means I need to check whether for each t, xt is ft adapted or not. Okay. Or if it is a natural filtration, then it is automatically adapted, because by definition ft, the sigma is generated by these things. Okay. So either it is given to you, it's a natural filtration, or it is somehow from somewhere it's come. Okay, that it's a filtration, it is given to you. Okay, with these things actually I need to define so-called the Levy process. Why I am defining these things, as I will see that Poisson process and then the compound Poisson process, all these things, they are basically Levy process. Okay, it satisfies the certain conditions and so on. Not only that, later on I will talk about called the Brownian motion, that is also Levy process. So Levy process is a general semi-martingale and so on, satisfy certain properties. So what is this Levy process? So a catalog, already you know what do you mean a catalog. That means it is right continuous with left limit exists. So it is not the continuous, but only right continuous with left limit exists. Adapted, that means for each t, xt is given ft adapted, where ft is the filtration given to you. Okay, say r value, I can define any any value, but for simplicity I am considering only the real value. Stochastic process xt such that t greater equal to maybe t is in your index set t. Okay, in particular I can think of t greater than equal to 0 because my this t is r plus. Okay, for simplicity actually we are considering, is called a Levy process if the following holds. So in particular actually we can start that x0 is equal to 0 almost surely, x0 is equal to 0 almost surely. Okay, and then x has independent increment. Okay, and third, it has stationary distributions. That is, the distribution of x of t plus s minus xt does not depend on t. Okay, x of t plus s minus xt does not depend on t. And most importantly, if you see that x is stochastically continuous. So if we write down this x, so x is stochastically continuous or continuous in probability. This is same as continuous in probability. That is what I can write down, that for every epsilon greater than 0, limit s goes to t, xt minus xs, this is greater than epsilon, take p, that is actually is equal to 0. Okay, for all t your say 0 is equal to capital T maybe. Okay, or in t capital T, whatever put it. If it is put it up to 0 to capital T, then you think, or maybe for all T is finite, something like that. Okay, so this is continuous in probability. This is continuous in probability, or sometimes called the stochastically continuous. Okay, so if a stochastic process satisfies these things, then we say that it is a Levy process. Now, if you recall all the things from Poisson process, no, it's satisfied. We have already proved it. This is from the definitions, and this one actually as a properties actually we have proved it. So Poisson process, it's a Levy process. It's a particular example of a Levy process. Okay. So we want to know more about this compound Poisson process. In particular, I am saying the compound Poisson process XT is a Levy process. So what I had to show that all these things are okay, because this is nothing but summation over I is equal to YI the IID, and it is independent of NT. Hence the all these properties 1, 2, 3, 4 and so on, they are fine. Only I need to show this property 4, that means whether it is stochastically continuous or not. So to show that, it suffices to prove something like that, that limit t goes to 0, probability of xt is greater than a, this is actually 0 for all a is positive. Okay, or you can put epsilon, because I just put without loss of generality, since it has these increments and stationary distributions and so on. From there actually I can think of, so I need to put t goes to 0, probability of xt greater than epsilon, that is equal to 0. If I show these things, then it is enough to prove that it is stochastically continuous. It is enough to prove that this part. Okay, how to prove it? So what is this quantity? Now if you conditions on nt is equal to n, then what I can write down, that the left hand side means limit t going to 0, probability of xt greater than epsilon. This is same as my limit t going to 0, summation over n is equal to 0 to infinity, probability of, so what is xt, I can put y1 plus y2 up to y of n. Okay, so this is greater than a, and then you take probability over nt is equal to epsilon, nt is equal to epsilon. Is it not? You just consider the condition on nt is equal to n, and then nt may varies from or kind of, it's a total probability you can think of. So from there I can have this part. Okay, so now one can change this limit, one can put inside. This is summation over n is equal to 0 to infinity, probability of y1 plus y2 plus yn greater than epsilon, because this is due to your dominator convergence theorem. Okay, now this one, so as limit t goes to 0, probability of nt is equal to 0, if you see, and n is equal to 0 from infinity, so from there you will see that this is equal to 0. And as I said that this inequality, this equality is because of the dominator convergence theorem. So what is dominator convergence theorem in particular? So what it says, that suppose I have a random variable xn, okay, this is converges to x almost surely. Okay, if I have xn is measured by some say y, and y is in L1 omega. What is L1 omega means? Basically this is integral over omega mod y dp, this is finite. Okay, it is integrable. So then what I can write down, that limit n goes to infinity, because you have done the major theorem and so on, no? So don't have to convert this theorem, actually you know there. Here it is exactly the similar kind of thing. So integral over omega xn dp, this is equal to integral over omega x of dp. Okay, so from here actually you will see that, because this is p of n 0 to infinity, and then this is a point measure. Okay, so that is why this integral is putting in a sum. So you can think of the expectations form, and then you change it to here, actually you will have this part. So because it is on probability, so that is less than or equal to 1, and hence y, whatever you have, that is always measured functions, no, integrable function, because any constant is integrable. Any constant is integrable, because omega, we have this measure of omega is equal to finite. So using domain convergence theorem, from here actually we'll see that compound Poisson process xt, it is stochastically continuous or continuous in probability. Hence the other two properties is follows, since nt, the Poisson process, it has independent increments, y is the IID and independent of nt, and so on. So all these two properties, and it holds. Hence the compound Poisson process is a Levy process, and compound Poisson process has many applications, even if in the model of insurance risk. Okay, so and not only that, you see that since my nt, it is piecewise constant, no, nt is piecewise constant, and yi's are the IID. So you'll see that the paths of the compound Poisson process, they are catalog piecewise constant functions. Okay, so paths of the compound Poisson process are catalog and piecewise constant functions. Okay, it's a piecewise constant functions. So we can ask the following reverse questions. I'm not going to prove it, because it is a Levy process, and they are the only Levy process with piecewise constant sample paths. So my claim is compound Poisson process is the only Levy process which has piecewise constant sample path. So which is given by the following properties, following proposition. So xt such that t greater or equal to 0 is compound Poisson process if and only if, sometimes I write down I double if, this is the meaning if and only if it is a Levy process and its sample paths, it is a Levy process and its sample path are piecewise constant. Okay, so this is the if and only condition. That means compound Poisson process is the only Levy process whose sample paths are piecewise constant. Okay, I'm not going into the I'm not going to the proof this theorem or these propositions. So but it is in my note, you can go through the proof. So if you have some problem, then maybe I can discuss, otherwise you can leave that part. Okay, but better to know that compound Poisson process is the only Levy process whose sample paths are piecewise constant function. Okay, So we want to know more about more certain properties of this random times TIs of Poisson process. So from there we'll see that these TIs, how we are connecting. So it gives you a measure on 0 to infinity, and that will declare as the random measure associated to Poisson process. This is simple to see how one can check it. Just look at what is your NT. NT we have defined that this is number of I such that Ti of omega, this belongs to 0 to small t, is it not? Because NT it counts the number of jumps. Okay, this is the I, that is the how many jumps in between 0 to t it is there. So this it counts the number of jumps and number of random jumps Ti and so on. So similarly I can think of that if my T is greater than S, then Nt minus Ns, this is nothing but the number of I greater equal to 1 such that this number of jumps Ti, this is belongs to S2 capital T. Okay, so this T1, T2, T3, T4 and so on, they form a random configuration of points on 0 infinity because they are positive. Okay, so that is the random configurations of 0 infinity, and Poisson process this counts the number of such points in the interval 0 t, is it not? So this counting process it defines a measure on R plus. So this counting process defines a measure. Since you know measure theory and so on, I'm not going to repeat this thing, because even if in probability theory also, whenever we are saying that omega p f, so this p, the probability is nothing but the measure, no? So it depends a measure on my R plus, means 0 to infinity in this form. So if you look at for any measurable set A, where A is measurable, how I can define my M of A or M of omega A, I can think of, because it is a random measure, because it is depending from my TIs, that is random. So M omega A I can think of. So this is nothing but I am defining all those I or the number of I such that my Ti of omega is in my set A. Is it not? So if you look at any measurable set or the Borel measurable set A subset of R, M of omega A, I am looking for number of I such that Ti of omega is in A. Okay. So this M is called, and it's a positive, MA is positive, this is positive, and integer value. Okay, and not only that, this M of A is finite, is finite for bounded A, is finite with probability 1, for bounded A, is it not? It cannot be infinite. This is just from your definitions of these things, and TIs are basically is the random configurations on 0 infinity, which is basically the interval times of Poisson process. Is it not? So now, not only that, I can say more on that, that if you look at expectation of M of A for any Borel measurable set A, what is this by definitions? I can write down this is M is equal to 0 to infinity, M times probability of M of A is equal to small m. Is it not? Now this is same as M is equal to 0 to infinity, M times probability of this, that M of A is equal to M. This is nothing but n of mod A. N is my Poisson process. N of mod A is equal to M. Is it not? Where A, mod A denotes the Lebesgue measure. So where mod A is the Lebesgue measure of A. You know what is the Lebesgue measures and so on. Already, since you have done MSc course and so on, so already you know. Okay. So now n, it's a Poisson process. So n of mod A. Okay. So this is the time you can think of. No, nt is equal to m. And now if you look at what is this, this is nothing but the expectation of n of mod A. Expectation of n of mod A. And what do you know that? This is basically nothing but lambda times t, and t is replaced by mod A. This is lambda times mod A. Mod A means is the Lebesgue measure of A. So expectations of this measure MA, this is lambda times mod A. Okay. So as I told you, this M is called the random jump measure. Associated to the Poisson process. So now in terms of this Poisson random measure or the random jump measure associated to the Poisson process, I can rewrite my Poisson process in the following way. N of t omega, this is nothing but m of omega and then 0 to small t, okay, which is nothing but integral over 0 to small t m omega d of s, because m is a measure on 0 to infinity, and hence actually I can write down n of 0 t is basically this is the measure, and then you integrate over 0 to t, means the total things actually you are looking for. In this way one can represent the Poisson process, or you can express. So the essential properties of M, so some properties of M, what is this? If you look at that, if you consider the two disjoint interval, okay, say this is your tj prime, and then this is tk prime, then if you look at m of this part and m of this interval, they are independent random variables. Okay, for any two disjoint intervals tj prime, tk prime, the random variable now, because m is a random variable, m acting on this tj to tj, m of tj to tj prime, then m of tk to tk prime. Okay, because this is the Borel set, no, one of the Borel set. So m acting on that is basically nothing but the real valued random variable. So they are independent if these interval are disjoint. Okay, and another property is that, so mtk, this is number of jumps of the Poisson process, m of say tk to tk prime. In these things, if you look at, so this is nothing but this is the number of jumps of the Poisson process in the interval tk to tk prime. So it's a Poisson random variable, and hence it's a Poisson random variable with parameter lambda times tk prime minus tk, is it not? Because that is the length. Because 0 to t I know that t, because t minus 0 is equal to 0, so here the difference is tk prime minus tk, so this is lambda of tk minus tk. That means m of tk prime, this is a Poisson random variable with parameter lambda times tk prime minus t of k. Otherwise that is the, if it is not the case, we cannot have this expectation of m of a is equal to lambda times mod of a. Because for any measurable set A, this is the Lebesgue measure of mod A, and if you look at the interval in this form, the Lebesgue measure is nothing but the length of that. No, that is why it coincides there. Okay. So for any measurable set A, this is for the distance, but for any measurable set A, if you look at MA, this follows a Poisson distribution with parameter lambda times mod A. The same thing is actually we are calculating here. Like compensated Poisson process, one can define compensated random measure. Because this compensated random measure is really important later, because whenever one to study, if one people try to model the physical phenomena and so on, there this discontinuity of the process comes into picture, and that one can integrate with respect to compensated Poisson random measure. Okay, so that is more important. We are not going into that details, but we just try to define what is the compensated random measure. So I denote like in the same m tilde, same notational thing, m tilde a, which is my m omega a, and then actually we are subtracting the mean. So in this case, mean is equal to lambda, because for n tilde we wrote down nt minus lambda t. What is lambda t? Lambda t is the mean of nt, the compensator. Okay, so in this case m, I have again the Poisson means this random jump measure. So expectation of m is lambda times mod a, that's why actually I am subtracting lambda times mod of a. And again you can verify the same thing else, like your compensated Poisson process. So expectation of m tilde of a is equal to 0. Second, variance of m tilde a, this is nothing but the variance of m of a, and actually you can check it, this is a times mod lambda. Okay, and another is that, another important property, that it is neither a integer valued, it is neither integer valued or nor positive, because same thing else, no, we are we talked about like your compensated Poisson process. So similar thing holds for compensated random measure. So this is sometimes called the radon measure. Okay, that means it's a radon measure. Oh sorry, radon measure is different. This is called the sign measure. Means it may take positive and negative all. This is the sign measure. Okay. So this is just looking for the Poisson process, and then actually we are analyzing what is the associated jump measure and so on. But then question is, can we generalize it to any arbitrary arbitrary setup, okay, where my R plus it may replace by some sigma finite measure space or not. You know that sigma finite measure space, so that you can write down as a union of some EI. So we say that E is a measurable space and E can be decomposed as is equal to union over EI over I, such that mu of EI, if it is finite for each I, then we say that it is a sigma finite measure space. Okay, like my whole R, it's a sigma finite measure space. Okay, or the real line. So I just try to put as a definition, and I'll write down the construction as a proposition. I'm not going to prove it, but just to know that this Poisson random measure, whatever we wrote down there, it is not holds only for Poisson process case, associated to Poisson process case, but it can be generalized to there, generalized to any general setup. So I put as a definition and then I'll stop. So Poisson random measure. So in the definition, whatever actually I'll try to write down is that whatever we have from my Poisson process, that is actually I will write down here, the main properties from there. So let omega f p be a probability space, and say E, this is subset of RD, and mu a given positive radon measure. Radon measure means it is a measure on each complex set, it is finite. Okay, radon measure means it's a measure on each complex set, it is finite. Okay, so like the Lebesgue measure, it's a example of a radon measure on my E and say mathematical of E. So a Poisson random measure on E. So in particular this E, no, previously this E is nothing but my 0 R plus. So now I am extending it to the other cases or the generalized case with intensity measure. Mu so is a integer valued random measure because there also we have seen that it is integer valued because it is positive and so on. No? So it is a integer valued random measure. So I can think of my M, this is a function from omega cross this sigma algebra to natural number, where omega A, this goes to M of omega A. Exactly in the same notation actually I am writing down, but here in a general case, not there, no Poisson process comes into picture here and so on, such that I have these three conditions. So for almost surely omega is in my omega, M omega dot is an integer valued radon measure on E. Okay, that is actually we have seen it, no, for any A that is a radon measure, that is a measure on my R plus, and B is what, that for any measurable set E subset of E, this MA is a Poisson random variable with parameter now mu of A, because previously it is lambda mod A, no, lambda times mod of A. So now I have mu measure here, so this is mu of A, that is probability of Ma is equal to K, whatever I have, this is e to the power minus mu A to the power K by K factorial for all K is in my natural number. Okay, and another thing is the disjointness, no. So if A1, A2 up to say AN are disjoint sets, no, then the random variable m of A1, m of A2, m of AN, they should be independent. They are independent. So whatever we have deduced for the Poisson process case, we are generalizing it to here, and then we are saying that it's a called Poisson random measure. Okay, so I'll stop now, just writing the propositions. Now question is, whether this I have defining this Poisson random measure, whether it exists or not. Okay, for particular case actually I have seen it, but for general case whether it exists or not, this is given by the proposition. Answer is yes, it exists. So that is called the construction of, yeah, I am not going to prove this thing, construction of, but it is better to know Poisson random measure. So for any random measure, mu on E, say subset of D, there exists a Poisson random measure M on E with intensity mu. Okay, that means Poisson random measure exists. And whatever we have seen previously, that if you look at the TIs, this is the random configurations of 0 to infinity, and NT, it counts the number of jumps, and from there actually we are seeing that, okay, one can define a measure on 0 infinity, which is nothing but that for any A is a Borel measurable set of R plus, that M of A is nothing but number of I such that my T of I is in A. Okay, so how many TIs lies in A? Okay, that is it counts that part. So associated that we have deduced that this MA is nothing but a Poisson distributed random variable. Not only that, if you consider the disjoint intervals or disjoint sets, then they are independent random variable and so on, and it follows a Poisson distributions with parameter lambda times mod of A, where mod A denotes the Lebesgue measure of the set A. Okay, and this idea one can generalize, where my R plus can be replaced by E, and then the Lebesgue measure may be replaced by this radon measure. Okay, because Lebesgue measure is a particular example of, radon measure is a particular example of Lebesgue measure, and so on. And construction of the Poisson process says that, okay, there exists a Poisson random measure on these things on a sigma finite measure space. Okay, I'll stop now.